All right, so last time we did integrals where basically the region that we were integrating over was a rectangle, right? So we had this nice box and this was our region, right? We have from A to B and then from C to D, right? So we could just do this integral from A to B, from C to D, whatever our function was, dy dx, or also with this integral, I said because we're integrating over a rectangle, we can also write this the other way around. From C to D, integral from A to B, f of xy dx dy. Right, I said this was no big deal. Um, so what if we don't have a region that's a rectangle? What if it's like a more general region, like something we see over here? So in this case, the integration still works basically the same, except we have to be really careful if we want to switch the order of the integrals. Okay, so for a rectangle, it's fine, but for something other than a rectangle, we have to be really careful about how we describe it. Okay, so that's what we're going to be doing today. Is we're going to be doing double integrals over a general region, um, where we probably want to switch the bounds, or we have to set up the bounds for ourselves. Okay, so let's get rid of that. No, 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 I don't want that. There we go. Okay, so here it says evaluate the integral of x plus 2y over the region D, where D is the region bounded by the two parabolas 2x squared and y equals 1 plus 2x. Right, so here we have the y equals 1 plus 2x, and here we have 2x squared. Okay, so what I'm going to do first is first I need to pick, do I want to integrate this first with respect to x or first with respect to y? Um, sorry, 1 second. Um, okay, so first I want to pick, am I going to integrate this first with respect to x or first with respect to y? So here, notice where they have this blue line indicated. Okay, so what I'm going to do is I'm going to pick a value of x. So I'm going to pick a value of x, okay, and then I'm going to integrate along this line, okay. So for this line, what is the, so I'm going to integrate first with respect to x. So I'm going to put x equals um, x plus 2y dx, and then we're going to integrate that with respect to y. Okay, so I need to figure out what are these bounds. And you'll see why I chose to do it in this order in just a second. Okay. Um, so what I'm going to do is for x, I'm going to pick a value of x, and then I'm going to say what is the smallest for that particular value of x. What is the smallest value of y? Okay. So here, the smallest value of y is 2x squared. Okay. So here, this is going to go from. Oh, I'm sorry. You know what? I'm doing this wrong. I said this backwards. I wrote that totally backwards. Okay, so when I said I'm going to integrate along this line, right? So first I'm going to integrate along this line, meaning that I'm integrating in the y direction. I'm integrating with respect to y. Okay, so I'm doing the same thing. So I'm going to pick a value of x. So x is fixed. X is a constant. And then I ask, what is the smallest value of y? So it might not have an actual numerical value. It might not be 1 or 3 or anything like that. In this case, the smallest value of y, it's the value 2x squared. Okay, and then what is the largest value of y? That's up here on this curve. That's 1 plus x squared, like this. And then And then, so once I have that, that gives me the area under this like slice. Okay, so it just gives us kind of like a Y slice of this region. Okay, and then I need to add all of those up from here to here. Okay, so again, it's kind of like I just found the cross-sectional area. So this was the cross-section area, and then I need to integrate all of those cross-section areas together in the x direction. Okay, so I'm integrating from -1 to 1. Okay, and this right here is the only hard part about these problems. Okay, the actual integration usually isn't that bad. It's usually actually pretty simple. Um, it's the setting up the bounds that's usually kind of hard. Okay, so let me just go ahead and evaluate this integral. So this is going to be the integral from -1 to 1 of so I integrate that with respect to y, so I get xy plus y squared, so that'd be 2 times y squared over 2, so those cancel out, from y equals 2x squared all the way up to, okay, 1 second, 2x squared all the way up to 1 plus x squared. Okay, when you say from here to here, you're pointing at something with your mouse. I really can't. Oh, do you not see the highlighter? So can you all see the? No. Oh man. Okay. Okay. Let's make that a bit darker. Is that better? Can you all see that? The highlighter on the cursor. Um, okay, so I integrate that with respect to y. So, let's see. So I integrate this, so I plug those in, and I'm plugging those in for the y value, so I have x times 1 plus x squared plus 1 plus x squared squared minus x times 2x squared, running off the screen, minus 2x squared squared equals, and that's from -1 to 1. Okay, so now I just need to simplify this and then integrate with respect to x. And this will be fairly simple. So this is x plus x cubed, and I'll go ahead and expand this out. So I have 1 plus 2x plus x squared minus 2x cubed minus minus 4x to the 4th dx. Okay, and then let's see what cancels out. So we have, so that's going to cancel out with one of those. Then we have plus 2x and plus x, so we end up with minus 4x to the 4 minus x cubed plus x squared plus 3x plus 1 from -1 to 1 dx. Okay, and then I just integrate this like normal. So this is going to be minus 4 over 5 x to the 5th minus 1 over 4 x to the 4 plus 1/3 x cubed plus 3 over 2 x squared plus x from -1 to 1. And so I simplify this, and we get minus 4/5 minus 1/4 plus 1/3 plus 3/2 plus 1. Then we plug in, so it's minus, and then I'm going to plug in the negative. So let's see if I can keep all these straight. Actually, let's just do it this way. Minus. So plug negative into here, we get -1. So it's going to be positive 4/5. That's going to be negative 1/4. Negative 1/3. Plus 3/2. And I'm out of space. Okay, so that's minus, so I plug in -1, and I get positive 4/5. Plug that in, we get minus 1/4, negative 1/3, plus 3/2, minus 1. Okay, so let's see, the negative, negative, so that's positive 1/4 and negative 3/2, so those cancel out. And then here, these ones kind of just double. So this gives me minus 8/5 plus 2/3 plus 2. So 3. For a final answer of, what is that? Minus 24 plus 25 plus 30 all over 15. It's 31/15. But yeah, okay, so all that work, I worked it out all the way. But the point is that setting these bounds up was really the important part. Integrating this was just like we did last time. Okay, you just do you just do the integral on the inside, and then you plug that into the integral, and then do that integral on the outside, the outer integral. Okay, any questions from this example? Don't see any. Okay, so let's do another one. So notice real quick, actually, hold on, sorry, let me go back to this one. Notice real quick, if I wanted to do the x integral first, okay, so I would have had to integrate this with respect to x first. I would have need to pick, basically fix a value of y and say what is the minimum value of y and what is the maximum value of y. I'm sorry, I said that backwards. What is the minimum value of x and what is the maximum value of x? And this actually would have been a big pain because here in this region, right, we kind of have this kind of two different sections. Okay, so that would have, we'll see some more examples where we don't, that'll kind of influence our choice of which one we do first. Okay, so this one, find the volume of the solid that lies under the paraboloid z equals x squared plus y. So this is what we're integrating, right? This is the function that we're integrating. Whatever we want, we're integrating x squared plus y squared dA over some region. Okay, and above the region, D in the xy plane, bounded by the line y equals 2x and y equals x squared. Okay, so they went ahead and plotted this for us. So there's actually two ways of doing this. And we'll go ahead and work both ways to see how they would both work. But what do you guys think? Should I do it for integrate with respect to, should I do the inner integral, let's see. Should I do dy dx or dx dy? Which integral should I do first? Which one should I do first? Which one should I do with the inner integral? Should that be dx or dy? Okay, so a lot of people are saying dx. So real quick, I don't think really in this example the answer matters too much. I'm going to do it both ways, but I'm just going to go with the one that majority said, and then I'll come back and do it the other way. So we're going to try to write this as the integral from x equals something to x equals, oops, not one, x equals something of this function, and then I want to integrate that with respect to y. Um, dy. Okay, so here I'm going to pick, so here, yeah, this image is kind of already drawn for it, but I fix a value of y, and then I look, what is the minimum value of y? That's here. Um, that's here. So this is the line x equals 1/2 y. So they just solved, so how did we get this? We solved for, just solve for x. Okay, and this over here, this was y equals x squared. So the minimum value of y is x equals 1/2 y. And then the maximum value of x, again, we solve for x and we get x equals square root of y. Okay, and then now I need to integrate this from the minimum value of y, which is down here, where they intersect. Okay, so this is where the two curves intersect at 0. And then I can also solve 2x equals x squared, right? So I move this over, I have x squared minus 2x equals 0. X times x minus 2 equals 0. So this tells me that they intersect at the point x equals 2, and then y equals x squared, so y equals 4. Okay, so that's where they intersect, so that's going to be my other limit here. So the minimum value of y, I'm integrating all of these slices from y equals 0 all the way up to y equals 4. Okay, so I integrate this and I get what? So I do the inner integral first. I'll scoot this back so I have more room. I'm going to go ahead and integrate. So I'm integrating this with respect to x. So this is going to be x cubed over 3 plus y squared x from 1/2 y all the way up to square root of y dy. I plug those in, and I have y to the 3/2 over 2 plus, let's see, so that's y squared times y to the 1/2, that's going to be y to the 5/2, minus, so that's 1/2 y, so that's 1 over 8 times 3 y cubed, right, because 1 over 1/2 cubed is 1/8, and then minus 1/2 y cubed dy. Why is y cubed over 2? Yeah, that should be over 3. Hold up. Yeah, that should be over 3. Thank you. Okay, so we can go ahead and simplify this a little bit. So this is minus, that's over 24. Okay, and then we can put this over a common denominator, so that's going to be minus 13 over 24. Right, so this is minus 12 over 24, so minus 1, so it's going to be minus 13 over 24, y cubed. dy. And again, y goes from 0 to 4. Okay, so we integrate like usual. We get 2/5 times 1/3 y to the 5/2 plus 2/7 y to the 7/2 minus 13 over 24 times 4 y to the 4th from 0 to 4. So now we just plug in 4. So we have 2 over 15, 4 to the 5/2 plus 2 over 7, y to the 7/2 minus 13 over, I'm going to put this as 6 times 4 times 4 times 4 to the 4th. And if I plug in 0, obviously I get 0 for each of those. Okay, so 2 over 15. Let's see, so square root of 2, square root of 4, that's 2. 2 to the 5, that's 2, 4, 8, 16, 32. Okay, so same thing here. Now I have 2 to the 7, so it's going to be 2 times 128 minus, let's see, so 2 of those can cancel out with those, and I have it squared. So that's going to be 13 times 16 over 6. And I'm just going to plug this into the calculator over in the chat. So we have equals 2 times 32 divided by 15 plus 2 times 128 divided by 7 minus 13 times 16 divided by 6. Oops. Equals calc. Okay, and so over in the chat you can see the approximate answer because I'm not going to work those fractions out. Okay, so now that we've done that, I'm going to go back and do this the other way. Okay, so if I wanted to integrate this the other way with respect to x first and then with respect to y. Okay, so we have the same region. The region does not change. Okay, and that's the thing that makes this tricky. Okay, so last time I integrated, or just now, I integrated this, and then I did 1/2 y all the way up to square root y. And I integrated this with respect to x, and then with respect to y. Okay, so real quick, if I was to just switch these around and do this, right, if I was to just completely just switch these around, this describes an entirely different region, okay? Yeah, so this describes an entirely different region that doesn't look anything like the region described above. Also notice, so this one should be a giveaway right here, that if I was to finish this integral, right, if I was to evaluate this integral and then evaluate this integral, the final result would have terms of y in it. And when I'm done with this integral, I'm supposed to have a number. There shouldn't be any variables left. Okay, so this isn't going to work. I cannot just flip-flop the integrals. Okay, I can only do that if it's a square or a rectangle region. But this is not, so I can't just flip-flop them. I have to be a little bit more careful. So let me redraw that region. So we had a curve that looked something like this. And this was the line y equals 2x, and this is y equals x squared. Okay, so last time we picked a value of y, and we said what's the minimum x and what's the maximum x. Now I'm going to fix a value of x and say what is the minimum y and what is the maximum y. So here, first I integrate with respect to x, so I fix x, and x goes from x, sorry, I'm integrating this with respect to y first, right? Because I'm going from here to here. So I'm integrating in the y direction first, integrating along this line first. So this is from y equals x squared all the way up to 2x, x squared plus y squared, dy, and then I integrate those slices all the way from here to here, right? So from here all the way over all of these slices, we're integrating them all together. So this is from 0, from x equals 0, all the way up to over here, which we said was x equals 2. And we did that by setting these equal to each other and solving. Right? That's what we have right here.
Mic off. Mic on.
Okay. So let's go ahead and start integrating. So yeah, so one thing to point out again is that the bounds, it's not like I was able to just flip-flop them. Okay, I had to go look at the region and consider what happens when I'm flipping, when I want to do this the other way around. Okay, but I integrate, so I have integral from 0 to 2. Now we're integrating with respect to y first, so I have x squared y plus y cubed over 2, sorry, over 3, from x squared all the way up to 2x dx, which is equal to the integral from 0 to 2. So that's going to be x squared times 2x plus 8x cubed over 3 minus x to the 4 minus x to the 6 over 3 dx. Okay, anything going to cancel out? This will simplify. So this is x cubed, or 2x cubed, and then plus 8/3, so that'd be 6 over 3. It's going to be 14 from 0 to 2 minus x to the 4 minus 6x to the 6 over 3 dx equals 14 over 9 x cubed minus 1/5 x to the 5th minus x to the 7 over 21 from 0 to 2. Okay, so we plug these in, and I get 14 times 8 for 9 minus 32 over 5 minus 128 over 21. Let's see if that's the same. I hope this is the same. So if I plug this into the calculator, I get, let's see, so 14 times 8 divided by 9 minus 32 over 5 minus 128 over 21. Cross my fingers. And I didn't type it in right. 14 times 8. calculate it? Ooh, okay, so it looks like I made a mistake somewhere. Okay, let's see what it should be. Two integral x squared to 2x x to the 2 plus y to the 2 dy dx. Okay, 14 over 9 is wrong. Okay. Oh man, that's not what I want. Okay, so it looks like my first answer was correct. Okay, and so we say, oh yeah. Okay, so that shouldn't be 14 over 9. That should be, oh yeah, that's over 4, and that's to the 4. So that should be 12. So here this is 12, and this should be 16. Okay, yeah, that looks better because that can cancel, so I get a 3 and a 4. And now I plug that into the calculator. So I have 14 times 4 divided by 3 minus 32 over 5 minus 128 over 21. And what does this give me? There we go. Okay, so they work out to be the same thing, even though the bounds look very different. Okay, even though this one has x's in the bound and even though this one has y's in the bounds, we don't just flip-flop them. Okay, we have to actually look at the region that we're interested in and figure out the bounds for ourselves. Okay, do y'all want to see another example of these? Because there can be some more interesting ones of these. Or should I do an example of the polar coordinates? Or would you rather just have an entire separate video on polar coordinates that I'll upload a little bit later? Okay. Okay, so I'll need to pull up a problem. So let me just say real quick, when you're doing this, I said the integration is usually pretty easy. So that's only half true. Sometimes when you can have something here that you can't actually integrate. So for example, I could do like integral like sine of y squared uh, dy dx. Okay, I don't know how to integrate sine squared or sine of y squared. Okay, that's just not something we ever learned how to integrate. I can't do a u sub. I can't do really any kind of substitution. I don't know how to integrate it. But if I flip the integrals, so now if I do this with respect to x first, and then with respect to y, this actually becomes possible. Okay, because I know how to integrate sine of y squared with respect to x because this is just a constant. So, so I can actually do that integral. and then I have to actually flip the bounds. Okay, so sometimes you want to flip the bounds because it allows you to integrate stuff that you wouldn't be able to otherwise. Okay, polar coordinates. So here, let's just remind ourselves we have x equals r cosine theta, y equals r sine theta. Okay, so if I have some function equals whatever, um, dx dy. So integrate this from x and y. So if I was to rewrite this function, and I want to now do this integral in terms of polar coordinates, okay? So I can translate everything into terms of polar coordinates. That's fine, right? So now I'm going to figure out how to rewrite this in terms of r and theta as my two variables, and I want to integrate this. I'll rewrite this function in terms of r and theta, and then I want to integrate those with respect to theta and with respect to r. So one thing that I have to remember is that, or that comes up, is that these two right here aren't exactly the same. Even if I would just literally just term for term change them. I have to remember to put an r here. Okay, I need to integrate this with respect to f times r. Okay, and what this means is that, right, if I have a square, right, so this is dx and this is dy, but if I change this into polar coordinates, it's going to look something like this. It's not actually going to be a square. Okay, it's going to be kind of this kind of slightly wedge shaped thing. Okay, so this change in area gets compensated for in this here. Okay, so we can kind of think of this as being the equivalent of, when you do the u substitution, right? So we would do something like u equals um, whatever, some function of x, and then we do the derivative, so we have du equals f prime of x dx. And then we would have to substitute this in. This whole thing right here is kind of the equivalent of this, or the r is kind of the equivalent of the f prime, um, where it kind of just comes up from the fact that we're changing coordinates. Okay, so that's a really easy thing to forget. We always need to put that r whenever we're changing into polar coordinates, and it just comes up from the fact that we're changing coordinates. Okay, let me find a problem real quick. Um, okay, so it says, here we go. So find the integral over this region, sine x squared plus y squared dA, where R is the set of points such that 1 is less than or equal to x squared plus y squared less than or equal to 16. Okay, so what does this represent? What does this region look like? So x squared plus y squared, that should make me think of radius, right? So this is going to be a circle where the circle radius is less than 4, right? So, and bigger than 1. So that's going to look something like this. totally not to scale, but this is going to be a radius of 1, and this outer one is going to be a radius of 4. And this is the region we're interested in. Okay, so this is clearly going to be easier to write in terms of the radius than having to deal with square root of 4 minus x squared. Right? That's not going to be fun to integrate. It's going to be a lot of trig sub and blah, blah, blah. So I want to do this in terms of polar coordinates because it's going to be a lot easier to integrate. Okay, so what do we have? We have r equals x squared plus y squared, and we know that theta equals arctan of y over x. Okay, we won't need that one for now. So just like before, I'm going to pick, okay, actually, so let me write this. So if I write this in terms of polar coordinates, this is going to be sine of r times r. Remember, I have to include that. And then I need to pick if I want to integrate first with respect to r or with respect to theta. Um, what do you guys think? D theta, dr d theta or d theta dr? Okay. So it's a little bit of a trick question because it really doesn't matter. So you guys say dr d theta. Okay, so let's just set this up. Let's figure out the bounds. And this is useful just for setting up the bounds, and we'll see that it doesn't actually matter which order I integrate in. So for r, we're integrating with respect to r. So here I'm going to fix an angle, okay? So let's just pick this angle with the 1, okay? So I'm going to fix this angle. What is the minimum radius? Right, the minimum radius is 1. The minimum r is 1. So that goes from r equals 1. And then along that same angle, what is the maximum radius? It's going to be 4. Why not? Oh, yeah, sorry. That should be r squared, and that's the whole point of this problem. Thank you. Okay, so now I need to know what is the minimum angle and what is the maximum angle. Okay, so the theta, right, so this angle, it starts at 0, and then I'm going to be going all the way around. So that's going to be from 0 all the way around to 2 pi. Okay, so now I integrate this. And actually, so here's why I was saying it doesn't matter. Notice real quick, this integral right here with respect to r, there are no thetas in it at all. So as far as theta is concerned, this inner integral is a constant, meaning that I can pull it out of this integral. So I'll do this and I'll change colors. So I have the integral r equals 1 to 4 sine of r squared r dr times the integral from 0 to 2 pi. I'll just put a 1 there, 1 d theta. Right, so really this is just the product of two integrals. So I can evaluate them separately and then just multiply the result. This right here, it's going to be 2 pi. All right, I integrate 1, I get theta, and theta goes from 0 to 2 pi, so that's just going to be 2 pi. This I need to actually evaluate. Okay, so I have the integral from 1 to 4 sine of r squared r dr. And let me do a u sub. So u equals r squared, du equals 2r dr. So if I need a 2 here, I multiply by 1/2. So I have sine of u du, right? 2r dr is du. And then, so when r is 1, u is 1. And then when r is 4, u is 16. So we integrate this. Um, Integral of sine is negative cosine from u equals 1 to 16, which is negative 1 half cosine of 16 minus, that's going to be plus 1 half cosine of 1. Okay, so altogether, oops, that. So altogether, when I multiply these two together, I end up with 2 pi times, actually I can factor out the 1 half, times 1 half minus cosine of 16 plus cosine of 1. Okay, those two cancel, and that's gonna be my final answer. I'll leave it like this. Okay. Let's see. Do I have time for another one? I have time for one more. Any questions from that one while I'm pulling up this next question? Okay, so it's gonna be not necessarily. That's what I'm trying to look for one now. Where it's not. Why did we do r squared? So the original function was x squared plus y squared. Oops. That's supposed to be r squared is x. R squared equals x squared plus y squared. So here, x squared plus y squared, that's just r squared. Okay. Let's try one of these. Okay, so it's integral from 0 to 1, integral from 0 to square root of 1 minus x squared. So that right there should give me a big hint that this involves circles, right? Because this is the equation for the top half of a circle. Okay, e to the x squared plus y squared dy dx. Okay, so I don't know how to integrate e to the x squared. That's one of the integrals actually we can't integrate. Okay, but maybe if I convert this to polar coordinates, right? Because that clearly looks like it's x squared plus y squared. That's gonna be r squared. Okay, so let's convert this to polar coordinates. So I need to look at the bounds here. Okay, so here we have y goes from 0, so it starts here, and goes all the way up to 1 minus x squared. Okay, so 1 minus x squared, that's the top half of a semicircle. So this is going to be our y. It's going to look like this. And this radius here is going to be 1. And then we go from 0 to 1, right? So that means that x starts here and ends here, right? So this is x equals 0, x equals 1. This right here is y equals 0. And up here, or this curve right here, is y equals 1 minus x squared. Okay, so I need to describe this region in terms of r and theta. Okay, so here theta, um, let me erase this. So this is the region I'm interested in. So theta here, it's going to start here and end here, right? So theta is going to go from what? It's going to go from 0 to pi over 2. And what about r? So if I fix a theta, it's going to start here at 0 and go all the way out here, where it's going to have a radius of 1. Right? Because if I solve this, I have x squared plus y squared equals 1, meaning r squared equals 1. Okay, so that means that here I have r going from 0 to 1. And then what am I integrating? I'm integrating e to the x squared plus y squared, so that's e to the r squared. So 0 to 1, that was with respect to r, and 0 to 2 pi, that's with respect to theta. Okay, so if it was just this, I don't know how to integrate e to the r squared, right? It's the same as integrating e to the x squared. But now I can actually do this because this is, remember, I need to include this r here. And this allows me to actually do a u sub that allows me to actually integrate this. And actually here, I have the same thing. Now note that this doesn't always happen, but it's a lot more common with polar coordinates, is that this doesn't depend on theta. Okay, so I can pull this out and write this as the integral from 0 to 1 e to the r squared r dr times the integral from 0 to pi over 2 d theta. Okay, so that doesn't always happen. It sometimes happens, but it's not uncommon for it to happen either. Okay, so this right here, that's going to be pi over 2. And then I need to evaluate this. So let's evaluate this. I'm going to do a u sub. Oops, nope, because I need to change the bounds. So again, I do u equals r squared, du equals 2r dr. So I'll need to multiply by 2 and 1/2. So I get 1/2 e to the u du from when r is 0, u is 0. When r is 1, u is 1. So that's 1/2 e to the u from 0 to 1, which is e minus 1 over 2. Okay, and then so this is this. This is pi over 2, meaning that this integral altogether gives me pi over 2 times e to the e minus, sorry, not e to the e minus 1 over 2, which is pi times e minus 1 over 2. Okay, so biggest hint on these, draw the region that you are trying to integrate over. Okay, I cannot imagine trying to do these problems without drawing the region. Okay, if you're not trying to draw the region and you're trying to do it in your head, I'm fairly confident that you're going to make a mistake. Okay, so draw the region. Should it be over 4? Yes, because I multiplied those together. That was the whole point of me rewriting them. Okay, so draw the region. Okay, then look for each variable, what is the minimum value and what is the maximum value for for that particular value, right? So here I look at r. What is the minimum r and what is the maximum r? It's not always going to be a constant. It might depend on x or it might depend on y or something like that. Um, like we saw in these earlier ones. It might depend on x, might depend on y, but we just fix the value of x and look at what is the minimum x, Or what is the minimum y? What is the maximum y? Or we do it the other way around. We fix an x. What is the minimum x? Fix a y. What is the minimum x? What is the maximum y? X. Okay. And then if you're going to switch the order of the integrals, make sure you're very careful to actually swap them properly. Okay, again, that means you have to draw the region and then think about what happens when you swap them. Okay. Also be careful about identifying the correct region that you're integrating over. So a common mistake is people think they're integrating over a different region than they actually are. Okay, so make sure that you're shading in the correct region here. Okay, questions? Otherwise, I will let you all go. You can go swap over to the Google Meet. All right, so I'll go ahead and end the live stream then.